my talk today, as you might see on the screen, is on Open RAN architecture and RAN intelligent controller, or RIC, where I'd like to touch upon the details of the overall architecture, functionality split between Near-Real-Time RIC and Non-Real-Time RIC, and also about the interfaces. So a few words about myself in the beginning. I've been involved in 5G development since 2012, and where I've been a work package leader of 5G Now project. Later, I was working as a RAN architecture consultant at Huawei R&D office, and I'm also a co-author of a book entitled From LTE to LTE Advanced Pro and 5G, published by Artech House. I did my PhD on radio resource management for LTE and 5G, and I've been also actively teaching courses to mobile operators, vendors, and system integrators on LTE and 5G, with the focus of air interface, RAN, radio resource management, and self-organizing networks. Without further ado, let me now go to the contents of our actual training. So we'll start with definitions on the ORAN elements. We're going to speak what are those to set up a scene. And then we are going to get into the architecture details and also implementation options once we have those in place. And then later, as Russell already mentioned, we are going to touch upon the specific element here, the RAN Intelligent Controller, or RIC. I'm going to discuss the general functionality of it, and then a split into non-real-time RIC and near-real-time RIC. And then we're going to dig into those specifically, together with the relevant interfaces, so non-real-time RIC and A1 interface, and near-real-time RIC and E2 interface. And of course, at the end, we'll have a summary so that we can summarize what we've been speaking about for the past 50 minutes. So I hope you will enjoy it, and I hope it will be useful for you. And let's get started. So let's start with the definitions and entities. It's not going to be an overview session on Open RAN as the last time, so we're going to get a little bit into the details today. While if you are interested into the overview-ish one, go to Intelefy's university, and there is the previous sets of webinars as well. But let's have a little bit of the introductory here with the Open RAN. As you might already know, this picture from the past webinars, the traditional RAN were in the previous, let's say, generations, also with 5G, but this is changing right now with the Open RAN concept, is where you have a big, let's say, a black box where you cannot get into the details. You only have exposed parameters that the vendors, the big vendors, choose you to have to, but you cannot get into the details. You cannot get into the let's say, information, and also the interfaces in between the individual elements. And this is changing with Open RAN, where mostly we are creating an ecosystem when the internals will be exposed in terms of open interface or open interfaces, with the split into central unit, or CU, DU, or distributed unit, and then RU, or remote unit, or remote radio head. What is more important is that the intelligence, the algorithms that are typically there were sitting in the traditional RAN, let's say, enclosed, they are being abstracted with the use of RAN Intelligent Controller, or RIC, the one shown in the orange color. Now, the Open RAN comes with disaggregation. We are disaggregating the base station into several sub-elements. And because of that, and because of open interfaces, it goes towards enlarging the vendor ecosystem, where more players can come into play and provide those. Open interfaces is the very important one for interoperability reasons and for having this bigger ecosystem. Decoupling hardware from software, so all that, except of course from the antenna, could be delivered in cloud. Intelligent management, that's the RIC. I'm not going to spend much time here because we are going to discuss that in details later. Lower capex, because we are trying to use the commercial off the shelf and putting on those the virtual entities that will have the functionality of a base station. And of course, because of all that, minimization of the proprietary solutions, as we will have to have interworking between all those entities. Now, speaking on the entity, so getting straight to the ORAN elements, what you can see here is the blue elements. They are defined by 3GPP and specifying the 5G base station functionality. And the orange and the yellow ones are related to the ones that are defined by the ORAN Alliance, the standardization body that is basically creating that architecture and bringing everything together, creating specifications. And now let's go from top to down, from down to top. The O cloud, by the way, the O everywhere means that they are the ORAN Alliance elements, and the O with the for all of the blue ones means that they are 3GPP specified entities, but with the O, with the adaptation, for example, with the use of E2 interface support and all the parameters that will need to be then fed into the RICs, they are called O thing to show that they are based on the ORAN Alliance specifications. Again, so we'll get back to the details. The O Cloud is basically a cloud computing platform comprising the physical nodes to host the ORAN functions. All of them pretty much could be in general the virtual entities. Of course, in the initial stages, the ORU at least, this is more expected to be a physical entity or physical network function, but then also ORAN doesn't prevent it to be a virtual one. And then, of course, the O Cloud needs to support software components with the operating system and basically managing all those entities and compute power and the memory storage for those entities. Then going a little bit up and getting to the actual base station, the ORU is basically based on the lower layer split or split 7.2 entity from 3GPP, basically hosting the low physical layer like FFT, physical random access extraction, and the whole RF part. The ODU sitting on top, that's the other, let's say, part of the lower layer split of the 7.2 split option, and on the other end of the open front hall interface, that is hosting radio link control, medium access control, and high physical layers, high physical layer parts. Then we have the central unit, so the one with the use of 3GPP nomenclature, again, split number 2, where everything on top of radio link control, so RLC, is sitting in the centralized unit. That is the OCU CP. So again, this is split into 2 more entities, the control plane and the user plane. The control plane is hosting the radio resource control, or RRC, and the PDCP part that is basically related to the RRC, where the security algorithms are running. Whereas the OCU UP is with the SDAP protocol and the user plane part of the PDCP. So basically also header compression, integrity protection, ciphering of the user plane packets. So this is basically the setup or the interface that is exposed towards the user equipments where the base station functionality sits. Now, what is extracted from this that was not present before is the Near-Real-Time RIC. That is a logical entity enabling near real-time control and optimization. We're going to see what the near real-time means, but basically it is relating to controlling the behavior of the smaller loop adaptation, relating mostly to the CU and DU. The near real-time RIC hosts xApps, and the xApps are functions or applications, separate applications that are independent of the RIC. There are open interfaces there that allows to, or open API to provide those by third party that basically are, in most cases, those are the radio resource management or self-organizing networks functions. But basically, this is the set of functionality that allows to manipulate the OCU, CP, and UP and ODU with certain actions. We're going to see the details of those, and some examples are things like traffic steering, mobility management, interference management, load balancing, and things like that. Then going up, there is a so-called SMO, or service management and orchestration. That is something that could be seen as a network management system. So that's a management plane. Everything below SMO is let's say a network, the RAN, and then SMO is the orchestration or management domain, management plane. Now SMO has the other, let's say, part of the RIC that is called non-real-time RIC. That is again a logical node enabling non-real-time control now, so not near real-time but non-real-time. We're going to see the differences between those. And it also includes AI ML workflow. So the functionality of the machine learning capabilities most likely sit there. Now, finally, there are R apps. So in contrast to X apps, R app is an application designed to run on non-real-time RIC. And again, that could be independent on non-real-time RIC. There is a defined R1 interface. And this is more of a, let's say, machine learning-based things that, for example, predict certain aspects. I'm not going to go to the details here, but we are going to see examples later on of the R apps. So with that, that's the basic, let's say, setup. We have the OCloud, on which we put the base station and the controller, the near-real-time RIC, on top of which we set the non-real-time RIC. Now, all those is specified by the ORAN Alliance working groups, where there are 10 of them, and each of them has a different, let's say, task to do. And in that particular discussion we are having right now, we are focusing on the first three. That's the use cases, the overall architecture, and the slicing aspects. And also working group 2 and 3, they are working specifically with those RICs. So working group number 2, non-real-time RIC and A1 interface, and near-real-time RIC and E2 interface is related to working group number 3. Of course, the other ones relate to other elements like front haul, like other interfaces, like white box hardware reference design, and the front haul, mid haul, and back haul. There are also some special groups for security, for example, or for testing and interoperability that popped up recently also in the ORAN Alliance. They are called special focus groups, by the way. One more thing in the introductory part, I encourage you to go to that web on the ORAN Alliance website. The link is provided here. In the ecosystem part, there is a technical priority document that is a document prepared by Deutsche Telekom, Orange, Telefonica team, and Vodafone, providing the priorities from the, let's say, operator side, with the setting priority of must-have and nice-to-have. And this is important because this is where the actual customers from the ORAN, let's say, ORAN RAN set, so that what is important for them. This is very detailed. It's an Excel file. In each sheet, you have a different sections like scenarios or CU/DU details, RU details, for example, what bands and what MIMO schemes does the RU need to support. And then, of course, there is a RIC part and RIC use cases. This is where we are focusing with that particular webinar on. So a little bit extract from here. How does it look like? It's basically, for the RIC part, we have, for example, a specific topic like, I don't know, AI ML model management, specific requirement, and also the reference to the ORAN Alliance specifications that you can download. They are free to download. You need just to register and comply with the, let's say, sharing policy. And then there is a description what that particular requirement means. So this basically document sets up the priorities for the ORAN Alliance to work on that, and for the vendors to work on those specific aspects. The P0 means they are must-haves. P1 means they are nice to have. For the RAPs, you, for example, have this specifically stated here. What is also shown here, that the ORAN Alliance here now doesn't exist at this point, but maybe there will be, maybe there will not be. Of course, there will need to be an R1 interface that is binding the RAPs to the non-real-time framework. But anyway, really encourage you to go there if you're interested in that part, because you can see what is the necessary elements of the ORAN architecture. Okay, so that would be the introductory part. Now a little bit about the architecture. We are going to see how those entities we discussed connect to the other with the interfaces, and also what are the allowed implementation options by the ORAN Alliance, how they could be combined in terms of implementation, how you can implement your nodes. So that's the overall ORAN architecture. We've seen pretty much all of those. The blue ones together with the OE node B, that's the base station, the 4G base station. It also could be incorporated into that, because as we know, the LTE or evolved LTE or LTE Advanced Pro, or basically LTE Advanced Pro from the release 15 is also under the umbrella of 5G system. It's also to be included under the ORAN architecture scope. So again, those are the 3GPP based elements, and also the blue ones relate to 3GPP based interfaces like E2, E1 between OCU CP and OCU UP, F1 between the central unit and distributed unit, and the other ones that are connecting to the core network and to the other base stations. Now, the Near-Real-Time RIC is connected to CU and DU over E2 interface. We are going to discuss that in details later on. And the Non-Real-Time RIC is connected to the Near-Real-Time RIC over A1 interface. There is also an orange one, so specified by ORAN Alliance again, an open front hall interface. And there is an O1 and O2 interface. Now, what are all those doing? So A1 interface is basically responsible to setting up policies from the management plane to the RAN domain. So it's sending that over A1 in the JSON, let's say, format, the policy and enrichment information, so some additional contextual information to the Near-Real-Time RIC, and ML model management. On the other end, there is a policy feedback going up. Then there is E2 interface, also very important, also going to discuss that later in this session, where from one side, the Near-Real-Time RIC, based on the policies, calculates and sets certain commands down to the base station. So it could use services and messages like monitor or suspend, stop, override, and control via those policies to the actual base station. We're going to see examples of those as well, and gets the data up and also the feedback. Now, the O1 interface, the open front hall interface, and the O2 interface are basically the FCAPs, so failure, configuration, security, performance, for different entities. So the O1 relates to the Near-Real-Time RIC and all the other entities except ORU, so OCU, CP, and so forth, for configuration, reconfiguration, registration, versioning, monitoring of the actual virtual nodes. And then from those, there are performance and resource updates that are going up to the SMO over the O1 interface. Same goes for open front hall M-plane. This is the FCAPs for the ORU. And then also, of course, from a different perspective and slightly different in terms of the functionality, because the OCloud are the actual, let's say, servers that host those. But this is also the FCAPs and management interface for platform resources and workload management. So for scaling up and down the resources for the actual ORAN entities. So that is the overall architecture. Now what we are going to discuss is how we can compose those. And by the way, what is important here also to mention is that the OCU CP, OCU UP, ODU, OE node B, they are called E2 nodes, mostly because they are connected to the E2 interface. And they can be combined in different, let's say, setups. So you are not binded to have each of those separately as a separate entity. They could be also combined, and this is what we are going to speak right now. Some selected ones, there are more of them, but I've selected some of them to show you the differences and show how the ORAN Alliance is looking at to those. There is a disaggregated network functions, let's say, way to implement that. This is basically just a copy-paste from a previous slide. Basically, each of the entity is a separate entity. Now, they could be aggregated. The OCU CP, OCU UP, ODU could be a single entity or a single network element, where then there is a single E2 node composed of all of those. There is another option where you incorporate Near-Real-Time RIC into that, and then you only have exposed the A1 interface towards the SMO, and that could be also, let's say, a node. Then we actually have an ODU being the E2 node, while the OCU is composed together with the Near-Real-Time RIC with internal, of course, interfaces. And there is also an option where all the nodes are aggregated. So this is basically a typical base station that you know from 4G world, for example, where you even have the Near-Real-Time RIC incorporated, meaning that everything is closed and you are back to the traditional RAN. What is important, though, is that you still have A1 interface, so you still can control the internals or control via policies how it behaves. But the Near-Real-Time RIC is implemented together. Now, what is important here is that having those different options, it is important that the A1 and E2 interface and then O1 are flexible in terms of how they address the specific nodes, because we need to address, for example, that this control message is to that particular node and that performance measurement need to go up from a different one. So there is, of course, a price to pay because we need to address those different possibilities with the design of the interface. So with that, that closes our part on the ORAN architecture, and now let's move to the RAN intelligent controller and the RIC. So a RIC is basically defined to enable E node B or G node B. We saw that the E node B, so 4G base station, is also part of that. Functionalities, some part of those functionalities that were traditionally hosted at the base station as xApp. So we just abstract out things like mobility management, admission control, interference management on the controller, which then enforces policies towards the RAN elements and control that with the external open interface. So you allow other companies to control the network. How does it look like? So we saw that there is a split between those. There is an RAPS sitting at the non-real-time RIC with non-real-time RIC framework. There are xApps sitting with the near-real-time RIC, and below there is a near-real-time framework. We are going to see examples of those later on. So non-real-time RIC provides configuration management analytics, basically takes a look on a helicopter view on the network, gets the AI-based feeds, and provides over A1 interface the recommendations to near-real-time RIC, and supports non-real-time optimization of the network and procedures. Now, A1 interface is the one that is used to send those policies, so provide policy enrichment information, ML model management, and gets the policy feedback back to the non-real-time RIC. Then the near-real-time RIC is a software platform, basically, to allow the xApps to control the RAN through it, with some management part that we'll see in a second, and enables near real-time control optimization of the elements via actions over E2 interface. We are going to see that in a second. Now, those examples like handover, optimization, radio link monitoring, advanced self-organizing networks like mobility management, load balancing, slicing policy updates, traffic steering, and interference management and things like that. E2 interface, already mentioned, is a RAN closed loop, so that's within the RAN domain, with the RIC control and policy towards RAN and getting the feedback up on the from E2 nodes to the near real-time RIC. Then there is the gray one that might be not seen, but is also very important as well. That's the ORAN interface, basically providing the data collection and control to the SMO so that it has the actual performance measurements from the E2 nodes. So that's it. Now, speaking of the functional split, we already saw that on top we have the RAPs, but we also have service and policy management. So the service and policy management basically creates those policies that are then sent over A1 interface, and also the AI and ML training model. What is important here as an input to the non-real-time RIC, we have the enrichment data, so additional information from the network functions, but also from external non-network functions, like, for example, external information that a specific user is a high priority than the other users that you not get from the network. And then we have, of course, the near real-time RIC with all the xApps we saw, radio connection management, interference management, quality of service management, but also the RAN and UE database. This is where the whole, let's say, the view of the network sits, and of course some management parts. We're going to discuss those in details later on, so don't focus on this right now. Now, there are 3 control loops, as you might be seeing and knowing already. The first one is called non-real-time control loop. That's basically related to the non-real-time RIC, with the latency much larger than 1 second. So that's basically when the policies are set, when the RAN analytics is gathered and performed, and then the AI and machine learning models are trained based on some, I don't know, longer data paths, so that basically you get more time to, for example, to see the trends of the network, how they behave over time or over day or over week or things like that. Then the near real-time RIC closes the near real-time control loop with the control loop of larger than 10 milliseconds and less than 1 second. And this is where the xApps are working on. This is how you get the updates, the feedback information, the policy update with the 10 millisecond minimum granularity and less than 1 second. And this is mostly related to things like connection management, where you need to decide if to move user from one cell to another one. That's in a typically 10 millisecond time range. And then we shall not forget about the real-time control loop that is less than 10 milliseconds. That's basically the real-time action, the resource management, the radio scheduling, your hybrid ARQ, your beamforming. This is where this is sitting in the E2 node, and specifically in ODU, where this is the RAN scheduler sitting in ODU in the MAC layer, deciding on the actual allocation. So near real-time RIC has only influence on the policy on those, saying, for example, we need to focus on, I don't know, 50% of resources for that slice and then another 50 for that. But this is the actual scheduler that is focusing on this and assigning resources to the users. Now, what are the differences between RAPs and xApps? We're starting with xApp sitting in the near real-time RIC. That is basically an application running inside the RAN domain, and they are designed to run in near real-time RIC. So it means they need to fulfill the API description that is provided for those. There could be one or more microservices, and at the point of onboarding, they need to identify and provide the information to the RIC, which data it wants to consume and what does it provide. It's similar sort of to the RAP. It also provides the information on the onboarding that it needs to get the data and what type of data does it provide. It's independent on the near-real-time RIC and might be provided by a third party, and the E2 interface is here very important because it provides the direct association between an individual xApp and RUN functionality. We are going to see how does it work, what's the procedure for this to work. Then RAP is an application designed to run on non-real-time RIC, so in the management plane, and provide some additional value-added services so that they help to provide those policies that the non-real-time framework is providing, including data analytics, AI, ML training, inference for run optimization, on recommending some configuration actions over O1 interface. So basically, they are very similar. They work on a different time scale. The functionality is slightly different, but the concept is similar. They are working as independent applications on the different parts on near real-time RIC and non-real-time RIC. Need to fulfill the requirements for the open API to be able to communicate with the other part of the RIC. So that would be the introduction to the RIC, and now let's move to non-real-time RIC and A1 interface. Here we are going to see the internals of the non-real-time RIC and some examples of A1 interface policy description. So in general, again, maybe being repeated, but non-real-time RIC is to support intelligent run optimization, providing policy-based guidance, model management, and enrichment information to near real-time over A1 interface. And that's configuration management, device management, and the other typical things for configuration control of the run. It might be seen as similar to EMS in legacy network that you know from the previous generations. The new radio units, basically what is important here is that they are self-configured by the non-real-time RIC, where we don't need to do the manual intervention. That's important specifically for the small cells where there are many of them and they need to be automatically configured. It allows to optimize the overall network, but taking into account the insights into network operations using the policy parameters, and can use AI model training inference to determine run optimization actions. Basically, the models are then fed to near real-time together with the policy and enrichment information. So this is the basic concept of non-real-time RIC sitting in the management plane. Now we're not going to go into the details of each individual element here because that's slightly, or not slightly, it's a big animal here. The important part are those different colors. So the part related to inherent to the non-real-time RIC itself are the blue ones. So they are basically used for managing the RAPs. The RAPs are external, as you might see, that's an open API to RAPs on top with the R1 interface. So all those elements related to RAP management, but then also the three important ones, those that create the things to be transmitted over A1 interface. So A1 policy functions, A1 enrichment information functions, A1 ML functions, they basically form the messages to be transmitted over A1. There are also parts in the SMO framework that is totally not into the non-real-time RIC. That's this other color, I don't know how it's called in English, but they are basically related to the non-real-time RIC, like O2 termination, O1 termination. They are inherent to SMO functionality. And there are the yellow ones. This is where there is a flexibility as of now, where they could be part of non-real-time RIC, and they could be also external to non-real-time RIC sitting in the SMO. They are not inherent, and those are, for example, AI ML workflows. So AI ML workflow functions could be either part of non-real-time RIC, as well as they could be external and then providing the information to the SMO service exposure functions. So that is the internal structure, pretty complicated, a lot of elements inside, and this is taken actually from the technical report. So as of now, the non-real-time function RIC is not yet very well defined. This is, let's say, an overall sketch on this. Now, some example RAPs, we discussed those. So what they could be. For example, we have 3 different RAPs here. The RAP R, RAP U, RAP Q on our ORAN interface to the non-real-time RIC framework, where the RAP R basically is the one to consume the O1 measurements. So it takes the information from the O1 for RF signal experienced by UV on serving and neighbor cells and UV location. And based on that, it estimates what's the future time prediction for the UV location and for the RF when the user moves towards a certain direction. So for example, based on the past information, when there is a user at that location, has that signal received from that base station and this from another base stations, then most likely he will have the other measurements when it's in that particular location. Then another one is a cell utilization predictor, basically that consumes the cell utilization, some amount of resources over the cell site over time, and outputs future prediction of the cell site utilization on the trend. So it basically could say, well, in the beginning of the day, there is a lot of traffic in that area, but then it moves around and then there is not much traffic because all the people sitting at their homes are moving to work. So there is less traffic now. And then RAPQ takes both of them and takes the measurements, the actual measurements, the predicted measurements, the actual cell utilization, the predicted cell utilization, and calculates the potential quality of experience. So it could say that the user taking into account that the user is here, that's the cell utilization, that will be the quality of experience, but also that could be for the future. So based on where it could be, that is predicted by RF signal predictor, what's the cell utilization potential there at that time, that is the potential quality of experience that the user might have. So this is sort of the things the RAPs are doing, and then based on that, the policy is created to be sent down to the Near-Real-Time RIC, for example, saying that, well, okay, if that user is going to have that particular quality of experience, if it stays in that cell, then maybe we should move it to another cell. And then based on that, based on the previous experience, based on the actual situation, based on contextual information, we get the actual data and the actual action that we need to take in the run. So that's a very, let's say, important and also very, on the other hand, very complicated but also interesting functionality here. Now, the A1 interface, it enables the non-real-time function to provide the policy-based guidance, mobility management, provides the interconnection between non-real-time RIC and the near-real-time RIC in the RAN domain. It is used to provide policies and get the feedback up, and also to provide enrichment information. For example, I don't know, again, that this user is of high priority, so we need to treat them differently. And that might be not coming from the network, but from the manual, let's say, setup at the operator's domain. Then this is based on the typical protocol stack where we have JSON files on top exchanging between near-real-time RIC and non-real-time RIC. Now, those policies as examples, the policies are non-critical to traffic. They have temporal validity. They are not forever. They handle individual UEs or groups of UEs, and we'll see how they could be grouped. And they take precedence over the actual configuration, and they are not persistent. Means that when you switch off and restart the near real-time RIC, then the policies are not set. Now, those policies are accompanied with the policy identifier that is assigned by non-real-time RIC, the scope ID that represents the group of things that are subject to that policy, like UE ID or a group of UEs, or a slice ID that also then reflects the UE, the quality of service ID, or cell ID. So they could be provided depending on the situation we have. and the change we want to do, and then it has the actual directives for the near real-time RIC to what to do with the UEID, with the UEs we want to change the behavior. Now, what are the examples? So, for example, we have traffic steering policies where, based on UEID, we might say, or based on slice ID, we might say that a particular cell shall or prefer or avoid or forbid. We cannot use them, or we might use them, or we need to use the specific cells. Now, examples. Well, that's quality of service, quality of experience, then traffic steering. So UEID number 855 shall prefer cells 39 and 40, and it shall be forbidden to enter cells 81, 82, and 83. And this is sort of a information coming from the non-real-time RIC based on the xApps, the RApps that calculate things like that, for example, to the near real-time RIC, and then near real-time RIC sends the command to the RAN domain. Well, please move that user from that cell to that cell because it is forbidden to use that. It's also for other entities like quality of service for UEID 855, quality of service ID 67. The priority level is increased to 50 or things like that. So those are examples of the policies that are then provided down to the near real-time RIC, to the network, based on which it takes the particular actions. So that's it regarding the upper part. Now down to the near real-time RIC and E2 interface. So near real-time RIC uses A1 and O2 for management and optimization of the RAM, and is responsible for optimization-related tasks, taking the data from all RAN types like macrocells, small cells, microcells, picocells, massive MIMO nodes, and all the elements. It uses a E2 interface to collect near real-time information, so a faster adaptation loop on a UE or cell basis, and controls those nodes again over E2 interface based on the policies we just saw on the A1 interface. The RRM functionality, whether it sits as an xApp or its capability of the E2 node, is subject to the control by near real-time RIC. And the actions it need to take, or it can take over E2, is monitor, suspend, stop, override, control via the policies. Now, what important thing, whenever a near real-time RIC is failing or E2 connection is broken, the E2 node shall not be broken as well. It shall function anyway. So it needs to support those functionalities. So if you have mobility management function being in the near real-time RIC as an xApp and it doesn't work, the connection is broken, the cloud is down, still the network shall be functioning, which means that the E2 node should have at least a small, basic default capability to do that, so that the network is still working. Again, the similar repeated information, what type of, let's say, functionalities here, like load balancing, radio bearer management, interference detection. And there is the base, there is a database that stores the near real-time state of the data, of the network, and feeds the RAN to train the AI ML models to be fed to near real-time RIC, and then that goes down to operate with the network. Again, the near real-time RIC interacts with non-real-time RIC via the A1 interface to get those models. Now that's the internal architecture of the near real-time RIC. It has, of course, the A1 termination to terminate the A1 from the non-real-time RIC. E2 termination to get the messages from xApps down to E2 nodes and back. The related messages to the xApp from what happened in the E2 node. We're going to see that in a second. O1, of course, terminates the O1 interface to the SMO layer. And then we have a shared data layer and a database that captures the state, that gets the data from the network, stores it there to provide to the xApps. The open APIs to allow basically to the xApp to operate and initiate the transactions over E2. So this is the xApp is invoking certain action to be transmitted to E2 node. The management services for the xApp, so basically FCAPs again for the actual applications. The subscription management, so that the new application can be onboarded, new xApps can be onboarded, or when they are deleted, to provide the unified data distribution through the messaging infrastructure, so a message bus through which we can distribute the messages based on how the xApps are subscribed to. And config mitigation function, very important one, basically to resolve potential conflicts, like, for example, one xApp is sending and requesting moving one user from cell A to cell B and another one from cell B to cell A because of conflicting things. Then those xApps, before they take an actual action, they need to ask the conflict mitigation to resolve that conflict and tell which is the precedent. So that's a very important part. And then, of course, the security scheme for xApps, so that we don't have malfunctioning xApps and something that are doing bad things. Now, the Near-Real-Time RIC can be realized as a centralized node. They can basically control the overall base station, or could be distributed, so control also the Near-Real-Time, the individual E2 nodes separately, focusing on certain aspects, and of course having those possibilities. There is, of course, pros and cons of them. Having the full-blown Near-Real-Time RIC, we have to take into account the overall and higher complexity of that, but then we have the overall view. Having the more specialized ones, then of course we need some interactions between them. That's one thing. Second, they can be optimized and they'll be very optimal, but they don't have the full picture of the network. Now, the final point for today is the E2 interface that is providing the connectivity between Near-Real-Time RIC and E2 nodes, exposing the E2 nodes data to the Near-Real-Time RIC, and enabling the control of the E2 nodes. And those services, already mentioned, nothing new. They could be report, insert, control, and policy provisioning to the E2 nodes. And of course, then the management and support functions like interface management, so for E2 setup with a particular node, and then updates regarding those services. So it looks as follows. We have Near-Real-Time RIC with xApps that are then basically controlling certain actions in the E2 nodes, the database holding the data from the xApp, and then there is an E2 agent that needs to be implemented in E2 node. That's where the O comes to OCU or ODU, because it needs to be capable of having this, and it needs to have implemented the E2 agent. There are functions that can be controlled by the Near-Real-Time RIC over the E2 interface from the xApps, and there are other functions that are not controlled and they're not subject to Near-Real-Time RIC services. Example procedure, Near-Real-Time RIC control, so how we can control and send the actual message to the E2 node that's taken from the Open Alliance specifications. Whenever something happens, the Near-Real-Time RIC detects the trigger, calculates things, the xApp does things, and then says, well, let's move a user from cell A to cell B. And that is sent from Near-Real-Time RIC to the E2 node. And that could be acknowledged, or that could be not acknowledged. So also E2 node doesn't have to always take the request and do that. It could also as well ignore that for some reason. So it's not that the Near-Real-Time RIC will have the particular influence on the E2 node. Example data that is coming over E2, UE specific network interface protocol, IDs, physical signal strength, radio source management, measurements, and then the details of the connection. So per DRB, per flow, per throughput, PRB utilization, PDCP, modulation coding schemes. So the detail, either the general things coming up from the measurements, but also the details taking out per UE, the specific per protocol performance. This is where the near-real-time RIC can really give the value by having all those and then having specific calculations based on AI, ML, can provide the more advanced decisions and more advanced resource management. The final point, interesting, at least from my side, the X2 operation, we're using the E2 control API procedure. So assume we have an xApp saying, for example, I want to move user A from cell A to cell B, mobility management functionality, for example. Then what it does is it assigns the unique request ID, and then it sends it both to E2 termination, because this is the E2 termination transmitting that to E2 node. And it also, but again, that is optional, can send it to conflict mitigation function in the same time, so to the E2 termination and or to E2, but let's say the conflict mitigation function. Then the conflict mitigation, of course, process that data, says, well, it's okay or it's not okay. It waits for some time, probably, checking if there are any other requests coming up from other functions, and then processing that, and then, okay, let's move with that. So near-RIC control request is going to the E2 termination, and then based on that, it can send a request. So E2 termination is sending that directly to the E2 node. So this is sort of an xApp sending the message to E2 node, but it needs to pass certain things. But of course, the conflict mitigation might say, well, stop, we cannot do that. Then there is E2 reject here. Now again, the E2 node might acknowledge, or well, it says, well, I'm not going to do that based on something. So based on that, it goes to E2 termination again from the E2 node, and more specifically, E2 agent at E2 node goes back to the E2 termination, and then that is sending back to the xApp so that the xApp knows if it failed or not. And then it also sends that information to the conflict mitigation function. So the conflict mitigation function also learns if it happened or not, and why it happened, why it didn't happen, to know all the details and then taking the decisions later on. So with that, I know it was fast, but it was a lot of information. Let me summarize all that. So going back to what we started, the ORAN Alliance defines the policies like OCU, ODU, ORU, Near-Real-Time RIC, Non-Real-Time RIC, SMO, OCloud, xApps, RApps. So all those different details. The base station is split onto this different functionality so that you have the possibility either to implement one, focus on one, or doesn't care about the other one, but also be able to provide the input like xApps or only providing near-real-time RIC. And interfaces O1, O2, open front hall, M-plane for the management of those different entities, and then E2 and A1 to provide and have the control loop on the run. The ORAN Alliance allows various implementation options where the different building blocks that were mentioned can be combined. That enables the flexibility of the implementation. You can work on OCU, or you can work on the whole base station. Then there is a RIC that provides control functionality to improve the efficiency and optimize network. Near-real-time RIC, when the RIC is split, near-real-time RIC, non-real-time RIC acts as a configuration layer sitting in the management plane and controls the near-real-time RIC via policies. And near-real-time RIC provides a software platform for xApp to manage the run. A1 enables the non-real-time function to provide policy-based guidance, model management, and enrichment information to the near-real-time function. And then based on the policies, so for me, it seems that this is actually, I don't know, some sort of a boundaries within which the near-real-time RIC can work and operate. And then xApps are working in that, let's say, region. And then E2 enables the connectivity between near-real-time RIC and E2 node supplied by different vendors and enable to control the selected functions in the E2 node. The E2 node, remember, needs to have the E2 agent implemented so that it can actually provide the control from xApps down to the to the base station. And with that, I would like to thank you for attention.